Okay, guys. So this video, I want to go over. It's just going to be a quick crash course into PES, which is photoelectron spectroscopy. So if you Google photoelectron spectroscopy, you can kind of see how it works, get a general idea. But we're really not going to get into the mechanics behind the machinery that gives us a PES readout. As chemists, what we need to be able to do is analyze the readout that we get from the machine. So you can talk about the mechanics right now, and get to learn that, but that's not what this class is about. The class is about the chemistry, and so I'm going to show you some of the charts, the PES charts that you're going to see, and how you're going to interpret those, and how you're going to answer questions about those. It's pretty simple. Once you have a really good understanding of electron configuration, and that the electrons are attracted to the nucleus, but the electrons that are closer, so the core electrons, the electrons that are in lower energy levels, are going to be more attracted to the nucleus than the valence electrons. And the further out you go, the further away, the higher the energy level of the electrons away from the nucleus, the weaker the attraction, and the closer you get, so the lower the energy level of the electrons and the lower the energy level sublevel, the more attracted they are to the nucleus. And in PES, we call that attraction to the nucleus, we call it binding energy. So what PES tells us is it tells us really how many electrons the atom has. It tells us, and it kind of tells us where they are within the structure of the atom by telling us how attracted they are to the nucleus. They tell us how bound they are to the nucleus. Okay, so again, if you just give PES a quick Google, if you go to images, this is what we need to be able to do. Given a chart like this, interpret it. So given something like this, interpret it, okay? We don't really need to know how the PES machine works, okay? But you can look at the images, read the diagrams, kind of get an idea. So really what it's doing, in the simplest terms, is it's firing different energies of light at an atom, at a sample, and it's figuring out exactly how much energy is required to remove the electrons. And we're not just talking about the valence electrons. So it's not just ionization energy we're talking about. We're talking about how much energy it is to remove a 3p electron versus a 3s electron. How much energy is required to remove a 1s electron, a 2s electron, a 2p electron. Any electron within the structure, how much energy. And we know the closer we get to the nucleus, or the lower the energy level of the electron, the more energy has to be put into that electron to remove it from the atom. All right. So, or another way to think about it is the closer the electrons are to the nucleus, the more attracted they are. So the more energy is required to pull the electron away from the nucleus, to remove it. Okay. So again, you're not going to have to draw this diagram or be able to describe what's going on. What happens is you'll be told that an element's been analyzed via PES. Here is the spectrum that popped up. What element is it? Or explain the peaks, explain what's going on here. Okay, so that's really what I want to get into today, because that's what you're going to have to do. Okay, and after you watch this, and after our lesson today on PES, you should be able to do your PES practice problems. Okay, now we're going to have some time in class next time to work on these as a group, but right, once you go over today's lesson, you should be able to break out the PES practice problems and start answering those questions. Okay. All right, so PES, photoelectron spectrum, or spectroscopy. And what we need to understand is it's going to be a chart that shows the binding energy of electrons within an atom. Okay, we know electrons are attracted to the positive nucleus, and we know via Coulomb's law, the closer the electrons are, so the lower the energy level of the electrons, the stronger they are attracted to the nucleus. Okay, so what would that mean? It would mean the more energy required to remove from their attraction to the nucleus to break that attraction to the nucleus, right? And then the other thing we should know is the higher the charge. So the more protons we have in the nucleus, the higher the overall charge of the nucleus, the stronger the attraction. Okay? So if I have an electron in energy level 1s and the nucleus has 33 protons and it's plus 33, that electron is going to be very much more attracted or more bound to that atom than if I have an electron in energy level 1s, but there's only 2 protons in the nucleus. So like a plus 33 nucleus is going to be able to attract a 1s electron a lot more strongly than a plus 2 nucleus. Okay, that kind of thing. All right. So again, how it works, you show you kind of blast the sample with different energies of light, and you see how much energy is required to remove each electron. Okay, and what you do is you get a readout kind of like this. Okay, now this is kind of sloppy. I'm just handwriting it. So again, what you're going to see like on the test is something like this, right? So a little bit easier to digest there. Okay, sorry about my handwriting. Okay, but it's going to look like this. You're just going to get a chart where on the y-axis it's going to say either relative intensity or relative number of electrons. So the y-axis is representing how many electrons are kind of being removed at that energy. Okay, so I have whatever number of this electrons being removed from this energy. It takes this much energy to remove it. Takes this much energy to remove these electrons. It takes this much energy to remove those electrons. Or another way, it's binding energy. So the electrons here are bound to the nucleus by this much energy. These are bound to the nucleus by this much energy, and so on, right? So whatever this peak represents, there's more electrons there, right? And then whatever this peak represents, there's less electrons there, okay? But one thing to really notice about PES, and I don't think I've seen it the other way on an actual AP test, so I think you can be sure not to check yourself, but notice that the x-axis, it's binding energy, but it goes from high to low. So we're going to have the bigger numbers over here. So it's not going to be 0 over here to a high number over here. It's going to be a high binding energy over here to a low binding energy over here. If for some reason that was reversed and you had lower numbers over here and higher numbers over here, then you would have to read the chart from right to left. But since normally they give it high over here to low over here, you're going to read from left to right. And that just makes it easier because we're used to reading left to right, okay? All right. So let's say this is a full, so there's a couple kinds of questions you have to answer. One is the full spectrum, okay? And one is partial spectrum. So let's say this was a full spectrum of an atom. This means it's showing all the electrons for whatever the atom is being studied, okay? So remember, highest binding energy means closest to the nucleus. So these would be the closest to the nucleus, so lowest energy level electrons, and this would be the highest energy level electrons. So over here, this would represent our valence shell, right? And these would be our core shells, okay? So highest binding energy closer to the nucleus, lower energy levels, lowest binding energy further away from the nucleus, the valence shells, okay? So here's the way to interpret it. Each peak represents a portion of an electron configuration, okay? So if I have a full spectrum, so this is the same one that I hand drew up here, okay? If you were asked to identify the element, you would just label each peak, starting from left to right, your normal electron configuration. So the first peak would be 1s2. Now the reason you know this has to be 1s2 is because you have a second peak. And the only way you could get a second peak is if you had the 1s full of electrons. And so what fills up the 1s? 2 electrons. Okay, if there was no peak over here and you didn't have numbers over here telling you how many electrons, then there would be no way to know if this was 1s1 or 1s2, right? But because we get another peak, we know that's 1s2. So we established this is 2 electrons, and this would be 1s2. The next peak would be 2s2, okay? The next peak after that would be 2p, right? Just normal electron configuration. And, again, I didn't have any numbers over here. So if I didn't have this peak here, all right, then I don't know if this is, maybe 2p4, maybe it's 2p5, maybe it's 2p6. But now I know it has to be 2p6 because I have another peak after it, right? So that means this peak must be full. So the next electron goes here. So this is 2p6. And now I know this is 3s1 because this peak, and I know I hand drew it, so it's kind of hard to, but this peak is half the height of this peak. So if this peak represents 2 electrons, this peak must be 1 electron. So this is 1s2, 2s2, 2p6, 3s1. And so what atom has that electron configuration? Sodium. So given this, if we were told this was the full spectrum, we could identify the element just by labeling each peak with our portion of the electron configuration. Okay? So again, let's remember, what kind of questions can we answer about PES? Okay? Well, we can identify, like if we're given a full spectrum, we can identify the element, right? We can write the electron configuration for the element. We can locate the valence electrons for the element, right? We can talk about relative numbers in each of our sublevels with the y-axis, right? That's the number of electrons. And then we can talk about how each peak or each sublevel, how much attraction it has to the nucleus, right? This is the highest attraction to the nucleus, and this is the lowest attraction to the nucleus. So again, closest to the nucleus, furthest away from the nucleus, all right? So if we have a full spectra, we can identify the element with electron configuration, okay? So let's go, go to your PES practice problems. Okay, I don't know, I'm not even going to read the question, but let's imagine this was a full spectrum, right? 1s2, 2s2, and then this would be 2p, 1, 2, 3, 4, 5, 6. So 2p6, so this would be neon. So which of the following elements might this spectrum represent? This would be neon. There you go. Okay, very, pretty easy. What if this peak only went up to here? And that would be 2p3, and so that would be nitrogen. Okay, great. All right. So given an element, let's sketch what the PES would look like. So phosphorus has an electron configuration 1s2, 2s2, 2p6, 3s2, 3p3. So the way we would sketch it is we'd have a peak representing each one. This would be the highest binding energy. This would be the lowest binding energy, okay? And a couple things to kind of look at. Remember, even though it's the same energy level, the p orbitals are a little bit further away from the nucleus than the s orbitals, so a little bit less binding energy, right? And the same thing happens over here. The other thing to kind of think about is notice like how there's like within the same energy level, there's not that much of a distance between the peaks, like between the 2s and the 2p and the 3s and the 3p, right? But as you go from energy level 1 to energy level 2, look, there's a much bigger distance. And notice that now between energy level 2 and energy level 3, it's a little bit shorter. And if we were to go to energy level 4, it would be a little bit shorter, and then to 5 would be even closer. So as you go higher in energy level, the distance between the energy levels gets closer and closer, okay? But so we would have 1s2 peak and then 2s2, and I would know to make this peak the same height as that peak because I have 2 electrons, okay? So then I have my 2p6 peak, back to 3s2, and so I know this peak would be as high as that peak because same number of electrons. But then my 3p3 peak would have to be higher than this because it has 1 more electron, but it would have to be half the size of that. And again, I'm just sketching it. Okay, if you actually had grid lines here, you could make it a little bit better. But that would be the idea. That would be what the PES for phosphorus would look like there. Okay. Now here's kind of a question. How would argon's PES compare to phosphorus? So there's 2 main differences that we want to understand, okay? So the first one is, well, if this were argon, right? Argon ends in 3p6 and not 3p3. Everything else is the same except for argon ends in 3p6. So one change that's going to be true about argons compared to phosphorus is if this were argon, this peak would have to be as high as that peak because it would be 3p6 and that would have to be equal to 2p6 in terms of height, right? Okay, so that would be one. But the other thing we have to understand is it's not just telling us how many number of electrons we have in each one. It's telling us how attracted they are, how bound they are to the nucleus. And what we have to understand about argon versus phosphorus is argon has 18 protons in the nucleus. Phosphorus only has 15. So phosphorus's nucleus is plus 15, where argon is plus 18. So the higher the charge of the nucleus, the stronger the attraction to the electrons. So the other difference besides this peak having to be higher is all of the peaks for argon should be shifted to the left a little bit because they would all be a little bit more attracted to the nucleus. So argon's 1s peak would be over here. Argon's 2s peak would be slightly over here. The 2p peak would be slightly to the left of this one. This would be slightly to the left, and this would be slightly to the left, and that tall, right? So there's two differences to think about. The height, because maybe you have a different number of electrons, but then also the shift to the left if you have more protons in the nucleus, or the shift to the right if you have less protons in the nucleus, because you're going to be more attracted, right? So if we were going to draw argon over top of phosphorus, so the solid represents phosphorus and the dotted represents argon, okay? So identical peaks just slightly shifted to the left because they would be more attracted to the nucleus, and then that last peak would be, twice as high because it's 6 electrons versus 3 electrons. But all of argon's electrons are more tightly bound or have a stronger attraction to the nucleus than phosphorus because we're dealing with plus 18 versus plus 15. Argon has a higher nuclear charge, okay? All right, so sometimes we'll talk about PES, like partial PES. So they'll give you a PES diagram, but it won't be the full thing. So if it's not the full thing, we can't identify the element. You'll be told what element or elements you're comparing. And a lot of times you're talking about the core electrons here. So we're not talking about the valence shell, we're talking about the core electrons, okay? So what if you were given a question like this? The following shows the PES for the 1s orbital of phosphorus and sulfur, okay? 1s for phosphorus and sulfur, okay? So phosphorus's valence electrons are at energy level 3, same with sulfur. So we're talking about the 1s electrons. So we're talking about the most core electrons for phosphorus and sulfur, because they both, in phosphorus's electron configuration, it has 2 electrons in the 1s, it's 1s2, and sulfur also starts out as 1s2. So they both have 2 electrons, so the height of their peaks should be identical. But what about the binding energy? All right, so here are the 2 peaks. One of these is phosphorus and one of these is sulfur. Which one is which? Well, you would have to know that this is the sulfur and this is the phosphorus, because sulfur has one more proton. So sulfur has a plus 16 nucleus, phosphorus has a plus 15 nucleus. So the 1s electrons in sulfur are going to be more attracted or more tightly bound or have a higher binding energy than the 1s electrons in phosphorus. So given this, and so you would know this would be the sulfur and this would be the phosphorus because sulfur has a greater nuclear charge, plus 16 versus plus 15. Okay? So both would have the same height because they're both 1s2. Okay? This is the 1s peak for sulfur, this is the 1s peak for phosphorus, but I know this is sulfur because it has one more proton. Okay? And the way you say it has one more proton, sometimes the answer is just it has a greater nuclear charge. Sometimes they'll throw in the word effective. We'll talk about effective nuclear charge as well, but it has a greater nuclear charge. So it has a stronger, higher binding energy. Okay, so sulfur's 1s electrons are more attracted to the nucleus because it has a higher nuclear charge. We're talking plus 16 versus plus 15. Okay, so that's the gist. That's what you need to take from kind of PES. And so you have these practice problems. I kind of answered this one already for you. That would be neon. let's look at a couple others, and then again, I'll let you work on it a little bit in class, or maybe you want to work on it over the weekend. Okay. So here's another one where they're just asking you to identify the element. So we would go 1s2, 2s2, 2p6. Now you know that's 6 because you could count, but you know that's got to be 6 because you get another peak. So 2p6, 3s2, and then this would be 3p1, 3p1. How do you know it's 1? Because it's half the height of the 3s2. Okay, so 3p1, what ends in 3p1? It's aluminum, right? So you know it's aluminum. Okay. Let me see another one. Okay, so here, okay, let's look at this one. This is showing, it's not a full spectra. This is lithium's 2s peak, right? And this is beryllium's 2s peak. So let's explain the difference. Well, why is lithium's 2s peak not as high as beryllium's 2s peak? Well, lithium ends in 2s1. So lithium only has one electron in the 2s sublevel. Beryllium has 2 electrons in the 2s sublevel. So that's why. So when we're talking about intensity, that's the difference in number of electrons, 2s1 versus 2s2. And then the binding energy. Why are the beryllium 2s2 electrons more tightly bound or have a higher attraction to the nucleus compared to lithium? Well, beryllium has one more proton. Okay? So which of the following best explains the relative positioning and intensities? So the positioning, so over here versus over here, is beryllium has a greater nuclear charge, but the difference in intensity is beryllium has one more electron in its valence shell than lithium, right? So beryllium has a greater nuclear charge, yes, than lithium, and more electrons in the 2s orbital. Yes, that's the answer. But let's go to the other ones. Beryllium electrons experience greater electron repulsions than lithium electrons. That's true because their electrons are paired. Beryllium's electrons are paired in the 2s sublevel, and lithium isn't. So that does create electron-electron repulsions, but that's not explaining these peaks. So that's not the answer. Lithium has a greater pull from the nucleus on its 2s electrons. No, this is showing you it has a weaker pull. Lithium has a greater electron shielding by the 1s orbital, so the 2s electrons are easier to remove. No, shielding is relatively the same as you go across a period. So, but again, that doesn't explain just the difference in these two PES. So the only thing PES can tell you is the number of electrons, and that's the height of the peak, and how close they are or how attracted they are to the nucleus. And then also, you know, the other thing is they're going to be more attracted to the nucleus if you have more protons, so greater nuclear charge there. All right? So you can give those a try. But again, it's something that we'll work on in class next time. But that's really just, that's PES. That's what you need to take from this. That's what you need to be able to answer. Let's just double check something real quick. I don't want to give you... So like if we look at our visible learning, right? So we're talking about this. So basically, we're finishing up 1-2, and part of that is PES. So we'll also do some practice with mass spec next class as well as a group. All right, and then we're going to be starting to talk about periodic trends and stuff. Okay, so hopefully you found that beneficial. We did talk about it in class. We'll do some more practice next time, and yeah, we're moving on. Okay.